Thank you. Good morning, everybody. I'm Kiriti Rambhatla, founder of Metakosmos. Just wanted to ask a question. Has anyone here ever tried to own a spacesuit? Buy it, essentially. You did? I was naive enough as well at the Ames Research Center in 2017. When I asked them, could I buy one, they told me I can't. And I tried to get a replica for myself, which was still in the range of $50,000 back then. So that was my motivation to start this company, to make these things accessible in the future. But today I'm going to be looking at why we need to understand biomarkers of our performance inside a spacesuit to be able to make these things affordable in the future. And just wanted to draw your attention to the history of human vitals, the discovery or inventions or creations of these things, and how they've had a profound influence on the development of the scientific instruments that were actually capturing that information over centuries. So you could argue that every time we created new markers, there was a need to improve the accuracy and efficiency of the scientific instruments that were actually capturing that information, leading to better health outcomes for us as humans. And we believe today is the right time, when spaceflight is at an inflection point, to create a standardized set of biomarkers for tracking so we could improve the instruments that actually capture them. And spacesuits happen to be one such components in that entire piece of human spaceflight. So when we specifically look at spaceflight and the human body, we could look at three fundamental categories of events that would be impacting our body, starting with variable G-forces. We've got space radiation and the use of spacesuits themselves that actually create issues for the body. We'll get into that in a bit. I was trying to get access to some videos of fighter jet pilots that train in those centrifugal chambers. Couldn't get access to them because of copyright issues, but I'd highly encourage you folks to look at those videos when people put themselves in conditions where they're testing the limits of up to 10 G. So someone who weighs about 100 kilos feels like they're weighing 1 ton inside those chambers. And you see a small tracker of the heart rate at the top, but I believe you've got to be able to track a lot more in those conditions for us to be able to conclude, statistically speaking, what is sustainable and healthy for someone to be in those kinds of conditions. And then space radiation is a very important thing. I believe with the limited data sets that we have, it's hard to pick an organ in the body that's not impacted by space radiation. And this is still an ongoing area of research, and these data sets are only accessible through NASA. So there is a need to have a lot more people to go through these conditions, and our understanding of these things will only improve over a period of time, provided we have the right instruments to access these conditions. On the spacesuit itself and the use of spacesuit, we've looked at some data points from NASA on the astronauts that have trained in these bulky suits over the years, and the issues they've reported while using the spacesuits are actually performing inside those spacesuits. And this is essentially a bidimensional problem. You've got the engineering side of things, which is not the focus of the conversation today, though we're working on that. The human side of things are very interesting, which relates to the biomarkers. So when you largely factor injuries that astronauts would have to sustain when they put on spacesuits, you could club the injuries into categories like musculoskeletal systems and everything to do with fatigue, because these structures are so heavy and they're weighing in on your body, and you tend to hurt yourself in different points. And we've summarized a few injury points, starting with the upper body, because that's where most of the injuries have been sustained. Starting with your shoulders to your neck and the spinal cords, and your arms and legs. So it is safe to say that there are certain injury hotspots on the body that are vulnerable to injuries when you put on really bulky spacesuits on yourself. So we have to design suits in a way that can protect these areas and at the same time help us understand what's happening to that particular area when someone's inside the spacesuit using it. So we've asked ourselves this question as to what does it really take to engineer the spacesuit of the future so human spaceflight as a whole becomes accessible and safe for people? Is it the right technical standards? Is it the engineering methods or the cutting-edge manufacturing processes? We believe the answer lies in building a data set of unique biomarkers that can help us capture relevant data points that will drive the process of spacesuit design and effectively craft sustainable human spaceflight programs. So, over the last couple of years, we've been able to identify certain critical aspects of the life cycle of human spaceflight and start mapping unique biomarkers that would help us start capturing information across these segments, starting with your biomechanical analysis to simulating the performance in extreme conditions and energy and fatigue profiles, impact of space radiation, and how all of that could lead us in the direction of preventing injuries to astronauts while they're in the pre-flight training conditions. And then you've got something about suit diagnostics, but I'll get into that when we start looking at some of these metrics. I can't jump into all the metrics today, but I'll give you some insight into the kinds of metrics that we're currently building on an application, starting with the suit configuration, where you need to understand the performance of the batteries that you put into the spacesuits. And if you could track the life of these batteries, you could prolong their duration, and so you could support the astronauts for a longer period of time. This was done in collaboration with QUT, where we've created certain metrics like the state of life and the state of health of the battery pack inside the spacesuit. On the biomedical side, this is very interesting because there's so many devices out there off the shelf that you could procure to get access to a lot of information on your body. But we wanted to go a little deeper and identify biomarkers for the health of the musculoskeletal systems themselves, and if we could do that in non-invasive ways. So the work is still underway, where we're trying to create a biosensor that could sit on the skin and start communicating about the health of the musculoskeletal systems. And we've got a program going on where we're trying to integrate Google Health's for applications, so you get access to the 1,000 Genome Project and the Cancer Atlas, which I believe maps up to 33 types of cancers in the public data set today. And this one's my favorite, the biomechanics of the astronauts inside the spacesuits, fundamentally boiling this down to the kinetics and the kinematics of the person inside the spacesuit. So when you look at kinetics, this is very interesting because we were trying to understand the spacesuit forces exerted on the body while someone's actually training inside them. We've done this project in collaboration with the University of Western Australia and DSTG, where they have certain exoskeletons that they're putting on the land forces to understand how people could operate heavy equipment on their backs. And the fundamentals of how you understand the forces exerted by an exoskeleton on the human body, very similar to what the spacesuit does to the body. So the next part is essentially kinematics, which doesn't get featured as much when people talk about spacesuits. Essentially, this is your joint angles, torques, and the range of motion. So the range of motion is very unique to every person, so we need to be able to design things that allow people to move freely inside the spacesuit. And then all of this comes down to training inside the suits. So there's a few tasks that NASA works on for people to be able to train in labs to essentially mimic what they would be doing on alien surfaces. So you could classify them as space station tasks or surface operations. But the idea here is, how do you actually move inside a suit and essentially establish certain activities that you have to carry out in space exploration. But the critical point here is to understand, what do we capture when people are actually training? Do you get an energy profile from them? Do you want to know the stretch factor of their joints? And what sort of energy expenditure is occurring throughout the activity? And then radiation outside the suit. So it's very critical for us to know how the suit is actually reacting to radiation and the impact of the organs while they're being exposed to radiation. And an ongoing work around the cognitive aspects, because this is important to understand when to abort a mission, when someone's actually being impacted, so we could track their attention spans and fatigue levels. So we're working with certain vascular surgeons who are helping us understand the blood flow in the body, because very little is known today, relatively speaking, on the flow of blood to different organs when the conditions of gravity change. Now, when you summarize all these things, what we've noticed is there's incredible amount of research happening across the globe in silos in all these domains, but for a sustainable human spaceflight, the assumption is these things need to be at one place where people could get access to this information at a cross-sectional level. So we are currently designing a portal called the Spacesuit portal, which is being built to be a NASA Class A human rated system, where you could actually get information across all those segments that I've just shown you, and also have the capabilities to store invasive data. By that I mean the bloods, urine samples, and everything that you could capture from that. And putting them at one place is critical because you could start accessing the health of the astronaut at a holistic level. And then the unique point about that application is a predicted performance of the simulation. So it will actually go back to your mobility matrix tasks and try to map what that predicted performance might be like on a certain surface. So this is just an example of how you could map the biomechanics or the cognitive aspects of the person training inside the suit, and then give them a profile of what their performance might be, for example, on the lunar surface. And this is going to be very helpful because you could prevent injuries or recommend course of action or training programs to people who might have to train better on their upper part of the body, or maybe train on their legs to sustain certain injuries that might occur. And so that's the biomarker side of things. And going back to my earlier slide around human vitals and how they had an impact on the instruments that were developed as things followed through centuries. We need to look at the design of spacesuits as a scientific instrument, or at least a platform that could actually have these scientific instruments on it. So it could start tracking these data points and help us improve them over a period of time. And so our base layer that you see on the screen that we're designing is intended to serve three major purposes. One being injury protection across all the areas that we've seen, and thermal management, so you could manage the fatigue levels, and most importantly, biomarker tracking. And I'm sure at this point, some of you might be thinking, isn't NASA doing all of this? Or are these data points not already available in the spacesuits that are being built? So I've just summarized the paper or document that NASA published, where they spoke about how the EVA training data sets are not consistent. And they've gone across the globe into all the facilities possible to capture data points. Any guesses as to how many facilities there are around the globe at this point? About 5. I think one of them is not functional, and 2 of them will not be as open. I guess in China and Russia, so they've had very limited data points to work with. And in most cases, it turns out they were tracking the expensive pieces of hardware, that is the suit. And when it came to the astronaut's health, in some cases they looked at photographs to make conclusions. So you could imagine looking at images and deciding what could be wrong with the astronaut. And this report, when do you think this report was published? 1970s? Show of hands, please. 1980s? 1990s? Just 6 years ago. So there is a need to standardize data points first, because what we track, we can obviously improve. So this applies to the entire life cycle, starting with your pre-flight training conditions to in-flight to post-flight conditioning as well, where you need to essentially build your strength back on 1G conditions. So if we could establish a standard framework for tracking the astronaut's performance through these biomarkers, we'd be able to design better suits and better conditions across the life cycle. So that is my presentation. Happy to take questions, because in most cases we usually leave people with more questions. So happy to take questions. Thank you.
Yeah. Thanks for the presentation, Kiriti, Gordon Cable, ANU. Just to clarify, could you please, if the suit is a gas pressurized suit for EVA, just tell me a little bit more about the pressurization profile of the suit.
Sure. So what we've shown is the base layer. We're calling it the sensor suit. And you're going to have a pressure layer on top, and then you have the final layer. So what we saw is the base layer plays the role of the liquid cooling element in the traditional EVA suits. But we do plan to have the gas layer, so it's not going to be mechanical kind of pressure. Thank you.
Hi. Have you thought of making your capability suit agnostic, so that they can fit on, thinking specifically commercial space, right? When there's multiple LEO destinations, there are going to be 3 or 4 vehicles taking you to multiple LEO destinations, and you might come back in a different vehicle than what took you, right? So we're working on talking about this tomorrow. How can we aggregate all of this data so that the data follows the spaceflight participants and those they stay in the vehicle? But that's why multiple suits, and I think it will be interesting if you could make it agnostic so that you could collect the data regardless of the suit. And the second question is if you could also use it on intra-vehicular suits, IVA suits, because that's where you see most of the G-low transitions, and most of the physiologic change happens on those races.
Yeah, thank you. I think the first question around making them agnostic. Yeah, I was talking to ASAM Space and some of the people in the US working on the vehicles. So the idea is to make this application open source at some point. One, open it to the medical community so you could add as many data points that you'd like to add into this. And then move it in a direction where it could connect and start managing fleet, because there isn't anything at this point that could manage a fleet of suits. I haven't used the slide, but we're intending to produce them at a big scale so you could track all these components if you wanted to. A lot depends on how the other companies would see this, because a lot of times it's a closed architecture. If you think of electric vehicles, people would want to have their own charging stations, although from a consumer point of view, people want the charging stations to work no matter which brand you're using. So yeah, we'd love to make this more of an open source architecture. And the second question was the IVA part. So this architecture, we're taking a layer-based approach for that reason. So this will be an IEVA, so it will play the role of IVA as well as EVA in the future, so it could convert into that. So the architecture has been designed in a way that 70% of it stays consistent for most of the spaceflight activities, be it pre-flight conditions or in-flight conditions, in which we're including surface operations. So it's intended to also work on land and underwater. So yeah, it will be a multi-purpose suit. Thank you.
Thank you for the presentation. Going back to how you open the presentation, can I buy a suit? And a more serious question, what's the business model? Like, are you going to sell a certain suits, or is it just technology you can license off?
Yeah, I think the business model would be the suit as a platform. So you could own the suit, depending on whether the banks would agree to buy into this arrangement where you could get the loan, so you could just pay for them on a monthly basis, so you get to own the suit, and then a subscription to the software so you could understand the performance inside the suit. So that's your standard software arrangement. So at this point, we've also filed a provisional patent, so a lot depends on how the American companies see this. If they see this as competition, most likely that would end up being a license agreement for them. If not yet, it would be a packaged service to the end consumer. I was quick so I could take more questions. So
So Kiriti Gordon again. This is all about translation of space to Earth, obviously. So I just wondered, space is a small market for spacesuits, really, isn't it, in total? What is the Earth market? What healthcare imperatives do you see on Earth that this technology might benefit?
Sure. So we've got 3 suit variants: Terra for land, Aqua for water, and Wirearm that goes up into air and space. And that version could also be customized for Air Force. So we started with the defense folks, where we explored options for the Navy divers that go up to really deep points in the ocean and all kinds of extreme conditions on Earth. Something I had no idea about, people who study volcanoes, volcanologists. And those are the kinds of applications we're exploring. Formula One, we had a conversation with them as well. So we could adapt the suit's architecture for use on a lot of use cases here in chemical, biological, radiological, nuclear environments too. So there's potential for this to be adapted for a lot of use cases on Earth. But we believe the space case will help us open up the limits of what we could essentially test on humans, and then everything else on land would then be a very, relatively speaking, easier use case to manage. So we could adapt it. So the architecture point that I was mentioning before, the suit is being designed in a way where you could customize the remaining 30% in terms of how they sit inside the layers that go on top of your skin and the external layers, and then you'd be able to adapt it for that specific use. And obviously switching the materials as well. So underwater is neoprene, on land is obviously nylon spandex and things like that.
Hello, hi, I'm Elizabeth Bates from Tasmania. It's fascinating. I was wondering if you could comment. I was quite fascinated by the idea of the sample transport inside the suit. It brought back a lot of emotional memories of, really hard blood draw and medical training at 2 a.m. and then you get the call from the lab that the sample's hemolyzed or clotted or both. Could you comment on the challenges and how those are being addressed with getting that sample back from wherever to home and a piece that a state that one can use?
Yeah, I think we've looked at essentially the biomarkers. So if you needed urine samples, how do you get them from the suit and then push it back to a mini lab of sorts? I think a lot of times people forget the intermediate steps, so we still need to take care of the traditional route of getting certain baseline biomarkers through bloods, and then you put them on the software that could help you expand on those data points and then start bridging connections. At this point, we're still working on certain biosensors that could give us these biomarkers that could help us understand certain information, which is very similar to what you'd get from a sample that's drawn invasively. But there needs to be a lot more work on maybe building a mini lab that works with the suit, where you could put your samples in that lab and then plug that back into the suit, which is more of an operational question. So this will be intended to go in the direction of being very independent on its own, so you could just use the fluids on your body to sort of feed the software from there on, so the sensors could capture that information. But if you need to go down the route of invasive testing, you would still need access to a mini lab that's actually working with the suit that you could pass information onto and grab that information back onto your software. That answers the question. Yeah. There's a few steps in there. I wish we could skip them, but certain things would have to be still done in the traditional way.
Thank you very much.
Thank you.